Previously, we learned that traditional vector spaces can have subspaces. That's true for abstract vector spaces also. And the way we test if a set is a subspace is exactly the same way that we test it for traditional vector space. Okay, so let's review that. So say we have a non-empty subset U of a vector space V. Okay, so remember, a subset is a set where everything that is in the set is also in the larger set. Okay, so pictorially, maybe this is vector space V. U is a subset of V, so everything in U is in V. Okay, so that means anything that's in U, any element in U, notice any element that's in U is also in V, right? Because V contains all of U, but not necessarily vice versa. There could be elements in V that are not in U. Okay, so U is a subset of V. We say this subset is a subspace of V. U is a subspace of V, provided that U is itself a vector space, given the same addition and scale and multiplication operations that the larger vector space V has. Okay? So it's just another vector space. It has all those lovely properties of vector spaces, that long list of properties that we've already explored. But because U is going to be a subspace, we don't actually have to check all of them. So if we want to check if a subset is a subspace, we could use the subspace test. We've already explored this in previous sections with traditional vector spaces. It's exactly the same here. If U is a non-empty subset of vector space V, then U is going to be a subspace of V if it is closed under addition and closed under scalar multiplication. So why is it that we only have to check those two properties? A vector space has a lot of properties. If U needs to be a vector space, why are we only checking two properties instead of that whole long list of vector space properties? Because U is a subset of vector space V, every element in U is in vector space V, which means that most of the properties of a vector space U inherits from V. V already has those properties. U is a part of V, so U inherits most of the properties, not all. We do have to check these two. If U also possesses these two properties, if it's closed under addition, if it's closed under scalar multiplication, then U is guaranteed to have all the properties of a vector space because its parent set, the larger set V, is a vector space. It inherits the properties. Okay, so let's take a look at an example. So my larger set, vector space V, I'm going to choose for my example P2. This is the set of all polynomials of degree 2 or less. With real numbered coefficients. So my coefficients A, B, and C are real numbers. We've already seen that this is a vector space. The subset I'm going to pick, U, is going to be all degree 3 polynomials again, with real numbered coefficients, but I'm going to add one extra condition. When I plug in number 3 in for x into the polynomial, I get 0. Okay, so in other words, 3 is going to be a 0 of the polynomial, or a root of the polynomial function. Okay. So first off, let's check if we satisfy conditions. The very first thing we need to do is make sure that U is a non-empty subset of V. Okay. Well, the subset part's easy. Clearly, U is a subset of V. Why? Well, because every element in U is also in V. V is all of the degree of all the polynomials degree 2 or less with real numbered coefficients. U is polynomials degree 2 or less with real number coefficients and some extra condition. So this is going to be some of the polynomials in V, but not all of them, right? But every polynomial here is a degree 2 polynomial or less with real numbered coefficients. There's an extra condition, but it does satisfy all the conditions that V has. So U is a subset of V. Okay. Second, it is non-empty. Now, there's lots of choices we can make here. Observe U is non-empty. Okay. A classic traditional choice is check if the zero vector is in U. The zero vector for the set of degree 2 polynomials is the polynomial where all the coefficients are 0. Okay. Clearly, if I plug 3 into x, 0 times 3 squared plus 0 times 3 plus 0 is equal to 0. I satisfy this condition. Because I satisfy that condition, I am inside vector u. That's not the only choice I could have made. I could have made 0x squared plus 0 plus 1x minus 3, right? I'd get 3 minus 3 is 0. That would also be in u. Remember, every vector space has to have the zero vector in it, an identity element, right? An additive identity. That's one of the properties of being a vector space. So if U is truly a vector space, if it's going to be non-empty, this is one element that it has to have in it. So very traditionally, this is the one we usually check first. Is the zero vector in the subspace? That's make sure that it's non-empty. If it's there, we're done. If it's not there, then it can't possibly be a vector space. A vector space has to have an identity, an additive identity, a zero vector. Okay. Finally, we need to check that U is closed under addition, that it's closed under scalar multiplication. So now let's do scalar multiplication first. Okay, let's take a scalar. I'm going to call it alpha. So a real numbered scalar and an element in U, an arbitrary element in U. So we have ax squared plus bx plus c in U. Okay, what I want to know is if I take alpha and multiply by this, do I still get a polynomial in U? Okay. Well, the key here is realizing that if I plug 3 into x, I get 0 here. Why? Because this polynomial is in U. And that's one of the conditions we have of being inside subset U. Okay, is that if I plug 3 into x, I get 0. Okay. We need to check that if we multiply by alpha, that still holds. So if I take alpha times ax squared plus bx plus c, well, clearly, if you want to get fancy and actually distribute the alpha, you can. But that's going to be in U, since if I plug in 3, well, a times 3 squared plus b times 3 plus c, we know that's 0 because ax squared plus bx plus c is in U. So I'm going to get alpha times 0, which is 0, which means when I plug in 3 into this polynomial, I get 0, so it is actually in U. Okay, there's nothing special about this polynomial that I've chosen. This would work for any coefficients a, b, and c so long as this condition holds. Okay, which means we're actually in U, which means U is closed under scalar multiplication. If I take an element in U and I scalar multiply it, the result is still in U. I took something that was in U, I scalar multiplied it, and I showed, hey, yep, it's still in U. Still has that property where if I plug in 3, I get 0. Okay? So that's condition 1 checked. I've checked that it is closed under scalar multiplication. Now I need to check that it's closed under addition. If I add two different polynomials, is the result still a polynomial within U? So let's check about addition. So for this, I'm going to need two potentially different polynomials in U. So let's go a1x squared plus b1x plus c1 and a2x squared plus b2x plus c2 in U. Now, both of these polynomials are in U, and remember the condition. If you're in set U and you plug in 3, you're going to get 0. That's a requirement to be in set U. So this means that if I plug in 3 to the first polynomial, if I plug in, I get 0. If I plug in 3 to the second polynomial, I get 0 because they're both polynomials in U. Okay? Now observe that if I add these together, I get what? a1 plus a2x squared plus b1 plus b2x plus c1 plus c2. This has to also be in vector space U. First off, it is a degree 2 polynomial with real numbered coefficients. But the more critical thing is when I plug in 3, I need to be able to get 0. That's the big condition of being in set U. So let's plug in 3. a1 times 3 squared plus b1 times 3 plus c1 plus a2 times 3 squared plus b2 times 3 plus c2. Well, because the first polynomial was in U, if I plug in 3, I get 0. So this is going to be 0, right, once I plug in the 3. Similarly, this is just the second polynomial when I plug in a 3, and we know because that's a polynomial in subset U that when I plug in 3, I get 0. So that will also be 0. So I'll get 0 plus 0, which is just 0. Okay, and that's exactly the condition I needed to be in set U. I needed to satisfy that condition that when I plug 3 into the sum, I get 0, which means the polynomial is in U. So what I've shown is that when I add two polynomials, any two polynomials in set U, the result is still in U, which means that U is closed under addition. Okay, we've done all the checks. We've made sure that U is a subset of V, that it is non-empty. We've showed that it is closed under scalar multiplication. We've shown U is closed under addition, which means that U is a subspace of vector space V. Not just any old subset, but a subspace. It is its own vector space. But it is a vector space that's a smaller vector space within the larger vector space V.